Imagine standing next to a machine so enormous that its tires rise higher than the roof of a family car. Now imagine that every single bolt, every steel plate, and every massive gear inside it began as ordinary rock buried deep beneath the earth. Giant tractors don't simply roll out of factories. They begin a journey that stretches across continents and takes months of engineering before they ever touch a field. Today, you're about to follow that hidden journey from the depths of the earth to one of the world's most advanced manufacturing plants. Think about this. A single high-horsepower tractor can weigh more than 25,000 kilograms. That's heavier than several African elephants combined. When its engine starts, the deep rumble shakes the ground, diesel fumes mix with cool morning air, and hundreds of precision-built components begin working together with incredible accuracy. But here's what nobody tells you. Before that engine ever roars to life, thousands of people around the world have already played a part in building it. Most people see a finished tractor and think of farming. Engineers see millions of dollars in research, thousands of hours of machining, and materials that have traveled farther than many people ever will. Over the next few minutes, you'll discover where every major component begins, why purity matters down to fractions of a percent, and what happens long before the first weld sparks inside the factory. And the first surprise lies hundreds of meters beneath the ground. Everything starts with iron ore. Huge deposits in Australia, Brazil, and Canada supply much of the high-grade ore used to produce the steel that forms a tractor's frame and chassis. Premium iron ore often contains more than 62% iron, reducing impurities and improving strength. Massive haul trucks carry hundreds of tons of ore at a time before trains transport it hundreds or even thousands of kilometers to steel mills. Inside a blast furnace, temperatures climb to nearly 2,000 degrees Celsius, hot enough to melt iron into glowing liquid that shines brighter than the setting sun. Coke made from coal removes oxygen from the ore, while limestone captures unwanted impurities that float away as slag. The air vibrates with roaring burners, sparks fly like fireworks, and the intense heat becomes almost impossible to imagine unless you've stood beside it. The factory doors slide open, and you're immediately hit by a wave of heat, the smell of fresh-cut steel, and the constant rhythm of machines working in perfect harmony. Every minute counts here because hundreds of parts move through the production line at the same time. Imagine watching thousands of kilograms of raw steel slowly transform into one of the most powerful farming machines on Earth. And this is where the real engineering begins. Everything starts with thick steel plates arriving from the mill. Powerful CNC laser cutters slice through steel up to 25 millimeters thick, using laser beams hotter than 10,000 degrees Celsius at the cutting point. Each cut takes only seconds, leaving edges accurate within fractions of a millimeter. The bright white sparks scatter across the factory floor while exhaust systems pull away the smell of vaporized metal. The freshly cut parts move to massive hydraulic presses capable of generating more than 2,000 tons of force. Under pressures reaching hundreds of bar, flat steel bends into perfectly shaped chassis components in less than a minute. Every movement creates a deep metallic boom that echoes throughout the building. What looks effortless actually requires years of engineering calculations. Now comes welding, where hundreds of robotic arms dance with incredible precision. Electric arcs burn at temperatures approaching 6,500 degrees Celsius, instantly melting steel together while shielding gases protect every weld from contamination. Bright flashes fill the air, molten droplets sparkle like tiny stars, and each robotic arm follows the exact same path hundreds of times every day. The finished frame emerges stronger than the individual pieces ever were. Next, enormous engine blocks made from cast iron enter the machining hall. Multi-axis CNC machines spin cutting tools between 3,000 and 8,000 revolutions per minute, removing tiny layers of metal until each surface reaches tolerances measured in microns. Coolant sprays continuously to keep temperatures under control while the smell of machining oil fills the air. What happens next surprised even experienced engineers. The engine becomes accurate enough that many parts fit together without any manual adjustment. The tractor may look finished, but this is where the toughest challenge begins. Every switch, every hydraulic hose, and every bolt must prove it can survive years of punishment in blazing heat, freezing winters, mud, dust, and endless vibration. Most people never think about this, but a brand new tractor must earn the right to leave the factory. And the first test starts with machines that never get tired. Robotic inspection arms move around the tractor with laser scanners capable of measuring dimensions within plus or minus 0.05 millimeters. Thousands of points are captured every second, creating a complete 3D digital model that instantly reveals even the smallest manufacturing error. Bright laser beams sweep across the glossy paint, while powerful computers compare every measurement with the original engineering design. If something falls outside tolerance, production stops immediately. Next comes the engine dynamometer. The tractor remains stationary while its engine works as if it's pulling an enormous load across a field. Engineers monitor horsepower, torque, fuel consumption, oil pressure, and coolant temperature in real time. The deep growl of the diesel engine fills the test hall. Hot exhaust shimmers in the air, and every sensor watches for the slightest sign of trouble. But here's where it gets truly extraordinary. Hydraulic systems operating at pressures exceeding 250 bar power heavy lifting equipment again and again for thousands of repeated cycles. Robotic test rigs simulate years of real farming in just a few weeks. Hydraulic pumps hum continuously. Powerful cylinders extend and retract without stopping, and every movement pushes the machine closer to its limits. Some tractors enter climate chambers where temperatures swing from minus 40 degrees Celsius to over 50 degrees Celsius. Ice forms across the body before powerful heaters transform the chamber into scorching summer conditions. Rubber seals, electronics, wiring and cooling systems must continue working without failure despite these extreme changes. Few machines on Earth experience such punishment before reaching their owners. Now that you've seen how a giant tractor is built, imagine multiplying that process thousands of times across the globe every single day. The worldwide tractor industry produces well over 2 million tractors each year, from compact utility models to the largest four-wheel drive agricultural giants. Together, this industry generates well over $90 billion annually, making it one of the most important sectors in modern agriculture. Without these machines, feeding billions of people would become dramatically more difficult. China produces the largest share of tractors by volume, followed by India, the United States, Japan, and several European manufacturing nations. Together, these countries account for the majority of global production, while specialized heavy-duty tractors come from world-renowned engineering companies serving farms across every continent. Every year, millions of components travel through an international supply chain before reaching assembly plants. It's a global engineering puzzle that never stops moving. Think about this. The global tractor industry directly and indirectly supports millions of jobs, including miners, steelworkers, engineers, software developers, machinists, welders, logistics specialists, and farmers themselves. Behind every tractor stands an enormous network of skilled people whose work often goes unnoticed. What begins in a distant mine eventually helps harvest food on the other side of the planet. Now let's travel back in time. Early tractors in the early 20th century replaced horses with noisy gasoline and steam-powered machines that were slow, heavy, and difficult to operate. Over the last 50 years, engines have become cleaner, more powerful, and dramatically more fuel-efficient. GPS guidance, satellite positioning, and onboard computers now allow some tractors to drive with astonishing precision, reducing waste while increasing productivity. And this is where the future becomes truly exciting. Engineers are developing autonomous tractors that can operate day and night with minimal human intervention. Artificial intelligence continuously analyzes soil conditions, fuel consumption, crop health, and machine performance in real time. Electric and hybrid power systems are also beginning to reshape the next generation of agricultural equipment. The factory of tomorrow may look completely different from the one you've just explored.